Hi, welcome to my channel, and today's topic is dimensional analysis, and it's also one of the most simplest topics you can think of. And although here for this tutorial is going to be, we'll consider the theoretical part, and the next year tutorial just after this is going to be based on calculations. So for this point, we have to take note of the little things that will give us a clear way to able to solve basic problems on dimensional analysis. But before going further, there are certain things we have to take note of. Let's say you have gone through the video. What are simply the expectations to students or to learners? One of the expectation here is the learner should be able to define dimensional method. The learner should be able to know variables which are dimensionless or quantities without dimension. And the learner should be able to know the uses of dimensions. And the learner should be able to know what are some of the limitations of dimension. Also, the learner should be able to know terms or quantities which are related with dimensions or which you can use to explain dimensional analysis. And as well as the learner should be able to know the dimension of fundamental quantities. And as I said from the previous video, the main three fundamental quantities are the length, the mass, and the time. So the learner should be able to know that the three fundamental quantities are length, mass, and time. So just after going through this video, these are some of the expectations the learner or the students must have grabbed after going through the video. So we move to the main point, dimensional method. What do we mean by dimensional method? Because like we have three fundamental quantities. We have length, we have mass, we have time. And the dimension of a quantity is simply the first letter of that quantity. Length here is the dimension of length is L. The dimension of mass is M. The dimension of time is T. So how these dimensions are related with one another is what we refer to as dimensional method. How length is related to time, or how time is related to mass, or how mass is related to time. So when these quantities are related, we refer that to be dimensional method. Take note, the dimension of a word is always written with the first letter of that word, but it is restricted with only the seven basic fundamental quantities, as we discussed from the previous video. For this case, the three main length, mass, and time, the first letters of those words, we consider them. So in this case, the first letter of length is L. So what I'm trying to say here is dimension is always differentiated from a word. Like if we have the word mass, we call it to be mass. But the moment we insert brackets within that word mass, so that word again, we cannot just call it as mass, we pronounce it as the dimension of mass. When a word is having a bracket, so definitely we use the word dimension to pronounce it. If we have velocity inserted with a bracket, so we call it to be the dimension of velocity. If we have density inserted inside a bracket, we call it to be the dimension of density. So any word which is inserted in a bracket, we call it to be the dimension of that word. So in this case, we can still use letters as F. The dimension of force here, we can we can insert brackets to it for us to have the chance or the ability or the go ahead to call it as a dimension of that force. You see, so in this case, anytime you want to write dimension of a word, make sure you insert brackets within that word. That's the first point. So there another time again, we can multiply two quantities. Like if we consider the formula of force in terms of mass and acceleration, force is defined as times the mass times the gravitational acceleration. So in this case, if we insert dimensions to those words, that means the dimension of force equals to the dimension of mass times A, or m times A. So in this case, so since m times A is a product, so the product of m times A, we can differentiate them into their factor. So therefore, MA, which has a dimension, equals to the dimension of M separately multiplied by the dimension of A separately. So when you have more than one dimensions of a value, you can multiply them separately. So if we move to the next slide, the dimensionless variables. There are certain quantities of variables without dimension. Like we consider the first one here, strain. Since strain is given here, so strain is a dimensionless quantity. Why we refer strain to be a dimensionless quantity? So in this case, strain is defined as the change in length all over original length. So both of the two quantities, numerator and the denominator, they both tell us about length. So therefore, their dimensions will be L all over L. So you find out that their dimensions will cancel. The dimension for the numerator, which is L, and the dimension for the denominator, which is L, will cancel out. Or the unit of the numerator, which is meters, M, and the unit of the denominator, which is meters, M, will cancel out. So this shows that strain has no unit. So any quantity without unit will refer to be dimensionless quantity. So if it does not have a dimension again, we will refer them to be dimensionless variables. So in this case, we'll consider again the next one, relative density, as the second word given here, relative density. Relative density, we can define it in various ways, as in terms of distance, or in terms of mass, or in terms of weight, or in terms of density. In basic, relative density is defined as the mass of a substance divided by the mass of equal volume of water. So in this case, if you look at the two values, the top is talking about mass, and the bottom again, which is the denominator, is talking about mass. You find out that the dimensions of both of the values will cancel. The dimension for the numerator, which is mass, and the dimension for the denominator, which is mass, will cancel. Or the unit of mass, which is kg for the numerator, and that of the unit of mass for the denominator, which is kg, will cancel. So therefore, relative density has no unit. So in simple form, any quantity without a unit, it is dimensionless, right? So in this form, we refer to those quantities to be dimensionless variables. So if we consider the next function, what are some of the uses of dimensions? We have various uses of dimensions. One of them will be, we use dimension to derive the relationship between quantities. How can this be possible? Which is going to be our next tutorial. Like if we consider speed, speed is defined as the distance over time. And the dimension of distance is L, and the dimension of time is T. So clearly, it has given us the relationship, or how we compare the two dimensions, as L for the numerator and time for the denominator. You see, so the first use of dimension, it tells us, or it makes to derive the relationship between quantities. The other use of dimension again, it helps us to derive units. How can we derive units? Let's use the same word. Speed is defined as distance all over time. Since distance is in relation with length, or height, or breadth, or width, or displacement, they're all the same. So their dimensions, both of them will be L. And for the denominator, which is time, is T. So therefore, speed equals to this distance all over time, which is L all over T. So L all over T, we can move the T up, which becomes LT raised to power minus 1. So therefore, the dimension of length is M, the unit of length is meters, and the unit of time is seconds. So that gives us meters per second. So this is how clearly we find units using dimensions. So the next use of dimension again, we use dimension to find the homogeneity of an equation, or it helps us to show whether an equation is correct or not correct. It clearly tells us the correctness of an equation. That's another use of dimension. So the other use of dimension, it also helps us to find a physical constant, or it helps us to find the physical constant or coefficient of certain variables. You see. And the next point again, we use dimension to convert a physical quantity from one system of units to another. So these are some of the uses of dimensions. After going through the use of dimension, what are their limitations? You see, because most of these theories, they have their limitation. So one of the limitation for dimensional analysis, one, this method gives no information about the dimensionless constant in the formula, like 1, 2, 3. If we consider the formula for period of a pendulum, because the period of a pendulum t depends on two quantities. One of them will be the length and the other is gravity, in short. So therefore, in a relation form or in an equation form, the period of a simple pendulum or the periodic time of a simple pendulum t equals to 2 pi the square root of L divided by G. You see, this simply means we can say 2 pi equals to that. So in this case, the 2 pi there the dimensional method does not tell us how that 2 pi clearly will tell us what is the significance of 2 pi from that equation. You see, so that's one function. There are certain equations we can see one as coefficients, two, three, or you can see e or any numbers. So the dimensional method does not give us a clear clue why those numbers are in that equation. You see, so that's one limitation. So the other limitation, this method cannot decide whether the given quantity is a scalar or not a scalar, or either it's a vector or a scalar. Because for an example, the dimension of velocity is Lt minus 1. And the dimension of speed is also Lt minus 1. In reality, speed is a scalar quantity and velocity is a vector quantity. But in this case, both of them, they have the same dimension. But if the words are not written, you just see Lt minus 1, we say for speed, and Lt minus 1, we say for velocity. If the words are not there, we cannot able to tell clearly that this first Lt minus 1 is representing speed, and speed is a scalar. Or this second Lt minus 1 is representing velocity, and velocity is a vector. So you see, so we have some doubts. There are certain things which the method, dimensional analysis, does not clearly tell us that. The moment you see a dimension, you can simply tell, oh, this dimension is a scalar quantity, or this dimension is a vector quantity, unless when it is different. Because like if you have Lt minus 1 and Lt minus 2, Lt raised to power minus 1 and Lt raised to power minus 2, we can know that Lt minus 1 can be either speed or velocity, while Lt minus 2 can be an can be simply by acceleration. We know that acceleration is a vector quantity. In certain form, we can able to differentiate, but in certain reality, we cannot able to tell clearly that this value is a scalar quantity or this value is not a scalar quantity. So this is also another limitation. So the other limitation again, using this method, one cannot derive relations involving trigonometric ratios or logarithmic functions. We cannot use this dimensional method in any way to solve any problem involving logarithm, or to solve any problem involving indices, or to solve any problem involving trigonometric ratios. You see, these are some of the limitations. So if we move to the next point, the next point is saying some terms used with dimensions. We have the first term to be dimension of a physical quantity. What is dimension of a physical quantity? You need to understand this word. Dimension of a physical quantity simply is defined as the number of times the fundamental units of mass, length, and time show up in a particular physical equation. You see? And we've also considered dimensional equation. It's just an equation which shows the physical quantity in terms of their dimensions. And the other one again we have to consider dimensional variables, as we discussed earlier on, are the physical quantity which have the dimension of variable magnitude. So if we continue with the same heading, the fourth one is dimensional constants. Dimensional constants are the physical quantities which have the dimensions but are constant in magnitude. You see, example, we take consider the speed of light. You see, it has a quantity, but in certain function is constant, because the speed of light, according to Albert Einstein, wherein it's related with mass, you see, and energy, so the speed there is constant. But in reality, speed in another form is not constant. So we consider again the other form, dimensionless variables. Simply are the physical quantities which have no dimensions, but changing magnitude. Example, we have plane angle, solid angle, and as well as strain. As we discussed, these values, they don't have any dimension, so they are dimensionless. So we consider the other one, dimensionless constant. Dimensionless constant is just like an ordinary number. Like pi is a number which in trigonometric we represent it as pi, which is seven, which can represent in trigonometry as 180 degrees, while in numbered form we represent pi to be 3.142. And we also have 1, 2, 3, 4, 5, 6. So all these values, we refer them to be dimensionless constant. And if we take the last one, dimensional formula. Dimensional formula simply shows how and which of the base quantities represent the dimensions of physical quantity. So that's that. So the next point, we go to the principle of homogeneity. The principle of homogeneity of equations is simply states that in any valid physical equation, the dimensions of both sides, in this form, the dimensions of the left-hand side must be the same to the dimensions of the right-hand side. If we consider one of the equations of Sir Isaac Newton, we say V, which is the velocity, equals to U plus AT. If you carefully find the dimensions of both sides, or we find the dimension of the left-hand side, we also find the dimension, the two dimensions of the right-hand side, we can see that both dimension for left-hand side and that of the right-hand side will be the same. So such format refer to be homogeneity, or the principle of homogeneity. We show that when the dimensions for both sides of the equations are the same. You see, so the next point again, we consider dimension of fundamental quantities. As we discussed, we have three basic fundamental quantities, which we have as the time, we have as the mass, we have as the length. You see, so these are the quantities. So time as a quantity, mass as a quantity, and length as a quantity. So in this form, what is the dimensions of these values? Since time starts with t, so the dimension of time is t. Since mass starts with m, so the dimension of mass is m. Since length starts with L, so the dimension of length is L. And what about their units? Time is measured in seconds, which we have as S, and mass is measured in kilograms, which we represent as kg, and length is measured in meters, which we represent as m. That's the point. So thank you all. So this is the end of this tutorial, and our next topic is going to be the applications of dimensions, how we can solve problems with respect to dimensions. Thank you all. Stay blessed. Wow. Wow.